Good morning. As she mentioned, I am an IT manager for Morgan State University. That's sort of one of the hat I have at Morgan State University. I like to think of myself as the it in IT for the Cybersecurity Assurance and Policy Center because I'm kind of the only IT person. I'm responsible for everything from the researchers, which is mostly PhD students, to the faculty, to all of the systems and everything that we use at the Policy Center. The second hat that I wear is I'm actually a PhD candidate as well. So this talk is more technical. It's more on the research that I'm conducting. That's more focused around zero trust and especially developing identities for IoT devices that doesn't typically support traditional zero trust technologies as we know them. So the zero trust security model kind of focuses on some areas being devices, identities, infrastructure, data, network applications, and for my research, I'm focused on devices and identities, and more specifically, as mentioned, IoT devices and developing identities for those devices. So I found this interesting image online that I thought really kind of captures and encapsulate what zero trust is all about, where we have whether it's a user or some device that needs to access. And the first thing you want to do is going to ask this question, who are you? We know that zero trust says that nothing is trust. We treat everything as if it's the internet. We trust nothing. So who are you? You need to show me some ID. Once that ID is shown, then we check for context. I like to call that the who, what, where, how, and sort of why. Why do you need access and from where and what's the purpose? And then once we are able to attest to those different things, then we provide the least amount of access that's required to perform the necessary tasks that they're trying to perform. So it's kind of say that zero trust is a security model that assumes that no one is trustworthy, even those that are already inside the network. So we're kind of moving away from this, the traditional network where it's the sort of the castle and moat. You protect the outside, but now you're protecting the inside of the castle, the individual rooms, which in essence is the resources. So for outline, we'll look at the sort of the background motivation for the research, formulate an hypothesis, look at our zero trust architecture to support identities, and we'll kind of look at our device identity classification because it's an important part in being able to provide identities for IoT devices. Our packet forward application, we have a short demo, if time permits, then we have our conclusion and follow up with questions. So zero trust kind of said that all communication requests have to be authenticated. Doesn't matter what it is, it needs to be authenticated. So we treat every device as if it's an untrusted device, which means that we sort of remove any sort of implicit trust that we have that have been long-standing that once you're inside the network, you can access everything. Where we focus on policy enforcement, and we move away from this perimeter-centric to a more of one that focuses on resource protection. And if you all are familiar with the NIST 800.207, their sort of best practice, of course, we know that zero trust is a methodology that integrates some ancillary system, including identity management, continuous monitoring, threat analysis, and so forth. So we integrate all different systems to be able to make effective access decisions. So what's the motivation for this research? That there's an absence of established standard to facilitate the implementation of zero trust for IoT devices. I've been to quite a few conferences and talked to quite a few practitioners that are actually developing software, and most of them, their solution is just put them in something and isolate them. And they operate on outdated identity and access management models, and also they lack the ability to support traditional zero trust architecture technology, primarily because the vast majority of IoT devices, especially when we're looking at really small sensors, they're optimized for battery consumption more so than security. So they operate on batteries. In a lot of cases, they're not very good with the batteries, so they try to utilize as less power as possible. So we sort of formulated this hypothesis. Can we leverage the communication pattern that IoT devices produce to predict the behavior and use that as the authentication for that device? And if we do that, at what cost? Meaning, what's the trade-off? So came up with this particular architecture. So Zero Trust architecture, we have sort of two planes. We have a data plane, and we have a control plane. Data plane, of course, your forwarding plane. That's where the decision is made where it's just simply for the data. The control plane is where the decision is made to what needs to be done with that information. So in our case, our open flow switches, so a lot of research is sort of built on Mininet, which is a virtual space that try to simulate software-defined networking. For our research, we actually use actual hardware. So we took a router and we installed OpenWRT on there, and then we installed a package called OpenVSwitch, which allows us to treat it as a software-defined switch. It then uses which serves as our data plane. Then for our control plane, we are using the Open Daylight software-defined controller, where, of course, that uses the OpenFlow protocol to communicate with the Open vSwitch. We developed a Java bundle, which is sits on the controller, and that interacts with a Flash web server that actually calls a variety of Python scripts to be able to perform the necessary operation that needs to be performed on the packet. So this architecture kind of outlines kind of how our environment is set up. At the very lowest level, we have our software-defined switch. Then we have Open Daylight, which is, again, the bundle, as well as Open Daylight controller is built on Java. We have our Flash web server, which talks to a database to be able to make the decision. So this flow table kind of goes through what sort of happens. So we send a packet to the network, and it asks the question, is there an existing flow on the switch? So software-defined switch works on flow tables, whereas traditional switches tends to work on access lists and things like that. It works on flow table. So it tries to find a flow based on whether there's certain matches or not. So if it does find a flow, what ends up happening, it'll perform the necessary action as specified by the packet. If it does not find a flow, then based on how we've set that software-defined switch up, it'll send that packet to the controller. The controller will now ask itself, is there a flow? If it is, then it writes a flow to the switch flow table, and the packet is sent to this destination. If it does not have a flow, then the module that the bundle that we set up will intercept that packet, and it will create a fingerprint from the information that it extracts from that packet, and it will compare it to what's in the database, as we saw in our previous image. If it finds a fingerprint in a database, then it will write a flow to the flow table of the switch and perform the necessary actions based on what that packet is trying to do. If it does not find a matching fingerprint, then it goes a little further. It asks a question, is this a new MAC address? Have we seen this device before? And if it looks at it and said, okay, this is a new MAC address, then it goes a little further. If it's not a new MAC address, then it performs device classification. And if it finds a match for the classification, then it'll create a new fingerprint to add to the database, write a flow to the switch flow table, and send the packet on its way. If it does not find a match, then it drops the packet. So this is just an architecture of sort of what our software-defined switch looks like. Again, this is built on a Linksys WRT 3200 ACM. We chose that because it allows us to actually flash it with the OpenWRT firmware and to be able to install the Open vSwitch package on there. What we did was we set up sort of a separate LAN for all of our IoT devices. We have 2 wireless radios. One is a 5 gigahertz radio, one is a 2.4 gigahertz radio, as well as a LAN. The reason why we chose this is because it allows us to do sort of wireless isolation, which means that every packet that comes in has to go through the software-defined switch, which means that we can actually perform the operation that we are trying to on it. Again, this is just a definition of our test bed. We have a total of 23 devices in here, as well as a few PIs, and we have our controller, as well as our controller, our database, and the collector PC. So, as I mentioned a little earlier, one of the most important things in being able to use this particular application is to be able to perform, is to be able to identify the devices. So what we have to do is perform a bit of learning, a bit of training. So we captured quite a bit of packets through our switch. And in order to do that, what we did initially was to set up pretty much a normal, what we consider a normal flow that allows everything through the network. So we knew what we had on there because it's a controlled network, and then we captured the packet. Then we performed some feature engineering by extracting the packet. Some of these are binary values, some of these are actual values that we actually extract from the packet header. And we perform sort of classification on the packet. So this just shows sort of a distribution of the type of packets that we captured through in the learning phase. So one of the things that we did was, because in our environment, we have several devices that are the exact same devices, meaning, for example, let's say we had 4 light bulbs. They're the exact same light bulb, same model, same everything. We use a method as proposed by a paper that we looked at. It was by Costas, where they aggregated like devices. So what we choose to do was to not just aggregate like devices, but to aggregate exact devices, meaning that they're the same devices. And the theory behind that is that if 2 devices are the exact same, their behavior should be the exact same. One device should not be behaving differently from another device if they're the exact same devices. They still need to communicate with the same cloud provider, and they'll behave in the exact same manner. So through our classification, we're able to achieve these particular results. So we had initially ordered 4 of the singlet light bulbs, which were the exact same. Throughout the process, one of the bulbs died. So we had to replace it. So I ordered another one thinking I was actually ordering the exact same one, but it turned out to be that instead of being a bright white, it was a daytime running light. And we're still able to classify it individually. So we actually left it individually. So if you see, we have where it says singlet light bulb and singlet light bulb 5. So they're able to actually classify each other individually, as opposed to having a lot of misclassification. So one thing I want you to kind of pay attention to is the F1 score, because that's really what kind of determines how well you're classifying, how well your model is performing, is the F1 score. A lot of times you can have very high accuracy, but at the same time, if you really look at the F1 score, you'll see that it's not very good, because if you have, let's say, in our case, we have imbalanced data, because IoT device doesn't always communicate at the same interval. Some communicate quite frequently, some communicate quite infrequently, so our data set was imbalanced. So, and even with the imbalanced data set, we're still able to identify and classify devices at a fairly high accuracy. So, as far as the fingerprint, so after we've performed all the cleaning of our data, we generated fingerprints. And how we did that was, so we took all of our rows, and we, in essence, remove all the duplicates, because obviously you're going to have duplicates because it's the same type of traffic being sent. So remove all the duplicates, and then from what's left, we generated this fingerprint. The fingerprint, the first part of it is just a MAC address in binary form. The second part of it is actually 16 binary features that we actually extracted from the packet header. And we put these together to make a 64-bit fingerprint. Yes, I know these are in sort of plain text. We can hash these to actually create a little more security, but just for my research perspective, we wanted to kind of leave these this way. And this is a fingerprint that gets compared when a device goes through the network. It actually extracts all this information, the Python scripts actually perform all the information, and then it compared to what we have in the database. So again, this is a kind of a flow chart that sort of explains exactly what happens when the packet actually reaches the controller. The previous flow chart kind of tells the overall story of the packet, but this one kind of goes into depth a little more of what happened on the controller. So it receives the packet, it checks to see if the packet it makes sure it's not a null packet, because sometimes there's a null packet that gets sent that doesn't have the information that we want. So if it is null, they kind of skip that extraction. But if it is a packet with information, we extract that data, we extract the payload from that packet. So when a software-defined switch sends a packet to the controller, it sends it as an open flow packet. So it's a packet encapsulated with an open flow packet. And so we have to extract that because that contains the information that we need. Then we send that over to our Flask web server, which then sort of takes over and perform the parsing, the feature engineering, the fingerprint generation, and kind of compares it to determine sort of what we're going to do with that packet. So this just kind of shows some screenshot as far as some of the things that we actually extracted from the packet. I actually have a short demo, so I'm going to skip through some of these because if we have questions, we can always come back to these. So one of the things we also wanted to find out was how much latency are we introducing to the operation as a result of using this method of authentication. So we took roughly 500 packets and look at the time that it takes to send the information to the send the packet to the controller, to perform all the necessary operation, and then write the flow back to the switch flow table. So we're introducing roughly between 58 and 59 milliseconds into that process, which is the blue point. The orange points on here is how long does it take the Flask web server along with a Python script to be able to perform the operation. So that's in the neighborhood of about 18 seconds. So that 18 seconds is technically actually included in the overall the additional latency that get introduced. So again, I'm skipping through these because the demo sort of has them. So I'm going to play this demo.
This is a demonstration of our Zero Trust Identity
I choose to make a demo because
application
sometimes
that will support
demos
IoT
make a video because demos don't always
in a Zero
work. You want
Trust
them to work,
environment. The first thing we want to make sure that our controller is in fact running, which it is. Additionally, I just wanted to verify that the AAA bundle is also running and active, because this is a very important bundle as it relates to being able to access certain API within the controller. So now that we've made sure that our controller is running, we're going to move over and we're going to start our login. Let's start the login. Additionally, we're going to also actually start the Flask application. So this application utilizes OpenDaylight as the software-defined controller. It uses Flask web server along with several Python script to perform the operation of the packet capture, the parsing, the fingerprint generation, as well as the classification of a new device introduced into the network. So we'll go ahead and we'll start the script, and we'll head back over to the logger. And then we'll move back over, and we're going to actually start our packet forwarder bundle. So the bundle is now active, and we should begin to see log messages starting to actually being generated. Additionally, if we look at our Flask web server that is running the Python script, we should also begin to see packets starting to traverse this network as well. So let's go back over to the login, and we'll go ahead and we'll stop this. Additionally, we'll also stop Flask from running as well. And we can see we have fingerprints that are being generated in here, as well as the packets being parsed and sent back to the application that will ultimately send this as a flow entry to the controller. Additionally, we included the hard timeout and a idle timeout, as well as a priority number. So the timeout, the purpose of the idle timeout is if there's no packet that is found for that specific device, then the flow will be removed from the flow table. And a hard timeout removes the flow table, the flow after this specified amount of time, which is 600 seconds or 10 minutes. So to find a flow that does not, where it did not find a fingerprint, let's look for one where it did not update the flow table. So in our case, of course, we generate the payload like we did in the previous one, send the request to Flask. Flask received a response that, or rather, Open Daylight received a response that no packet data was provided. And as a result, it skips the flow entry. If we look at Flask, you can see that the fingerprints that are being generated, if we look at one that where it did not find a matching fingerprint, all of these are matching fingerprints. Okay, so here's one where it did not find a matching fingerprint. So we see that we have the fingerprint that's initially generated from the packet, turn the string up to all zeros, and then I find one, what goes into the next part of the pipeline and check to see if this device is a new device or not, returns the same MAC address, which means it's not a new device, and as a result, the flow table will not be updated. And we have this 400 error message because it did not find what it needs to find, and that's what it sends back to the Open Daylight bundle.
Okay, so that's just a demo that sort of kind of explains what's happening. And so from a conclusion standpoint with experiment, we have shown that through classification, we can use the IoT device behavior to provide authentication. From a classification algorithm, we use random forest. We looked at some additional ones such as k-nearest neighbor, we looked at decision tree. Random forest seemed to perform the best because we're dealing with multi-class problem. So from a latency perspective, like I said, we saw roughly 58 milliseconds of additional latency to perform authentication. We can actually even lower that some because initially when we looked at made the video, we were actually capturing some additional fields that we don't need to capture, so we can actually remove those to actually improve or reduce the amount of latency that we see, even to a much lower level that will be tolerable in order to be able to perform device authentication and access control for IoT devices. And a question, so we still have to answer is how do we handle misclassification if we introduce a device into the network and it does not classify this device as being a legitimate device. So one option that we have now is to just sort of put it into an isolated subnet with just limited functionality. That's something that's been proposed by some other individuals, but we're still sort of looking at that part of it. And I'll take questions.
Oh, we got one for Ryan here.
Hi, this is great. I was considering how larger flows might be addressed by the hard timeout of the flow table entry. Have you looked at possibly categorizing the data to know when you could extend the hard timeout, or also how does that hard timeout affect maybe large data flows? Do you have to reset up the TCP session, or how might we extend this to be able to handle that?
Yeah, that's something that we're sort of still looking at, and because especially IoT devices, a lot of time some of them use polling, where they'll keep a TCP session open for a specific period of time. So we're still looking at what is the reasonable amount of time where it's not too short, but it's not too long, because part of the issue that we want is for this to go back through reauthentication periodically. Because if we're not going through reauthentication, then it's not providing the sort of authentication it needs to perform, which is kind of what we're looking at, is to be able to perform the authentication periodically. So we're still looking at what is the acceptable amount of time to be able to have it so that, like you said, when we have long TCP sessions, or that we keep it open long enough so we're not, having retransmission and things like that.
We have time for one more question.
Hi, great presentation. Can you tell us more about how the system might support least privilege authorization once the authentication step has been performed? Is that at the network level, or what are the options for that?
So what we're doing is, from a flow perspective, is it looks at the fingerprints that's in the table, and then it writes a flow. So the flow is going to tell it, okay, from what source IP or from what source MAC you can access a source MAC and over what port. So that's sort of what's providing the sort of least privilege in that sense.
Thank you so much.
Thank you.